All right, any questions about anything before we get rolling? All right, we've got another sort up to take a look at. Unlike all of our previous sorts, which have a big O of n squared merge sort, it's going to outperform with n log n. First step is to recursively divide the array into small sorted pieces. All right, so for an in-memory sort, we're talking about arrays of length 1 or less. So we have a pair of sorted arrays. We'll merge those back together. All right, and we'll just go ahead and repeat this process until the whole array is sorted. Okay, so all right, so let's say we're going to sort 5, 2, 7, 1, 3, 9, 4, 6, and 8. And we make that actually 8, 6, 4. So what we're going to do is just keep dividing the array. All right, 0 plus 9 gives us 4, so we'll go and grab first 5 elements. 0 plus 4 gives us 2, so we grab the first 3 elements. Repeat the process, keep dividing. And now we have 2 single element arrays. All right, so we'll go ahead and color left orange and right red. What we're going to do is compare. Right, so the merge process, expand on that up here. Merging step. Compare the first element, each sorted array. Take the lower of the 2 and copy that into another array, advancing the front of the list pulled from it. And we'll keep pulling from each list until that list is empty. All right, so compare 2 to 5. Go ahead and take 2. Compare nothing to 5. We'll take 5. And that gives us a sorted list. All right, so I don't have another list to merge just 2 with just yet. So we'll go back up recursive call stack and we see we have this 7 left over from before. 7 is a sorted list. By definition, a one element list will be sorted. Compare the fronts of each array, 2 versus 7. We'll take 2, 5 versus 7, take 5, and 7 versus nothing, then we will take 7. All right, so that takes care of the first 3 elements, and we'll keep working our way back up. Left off here with a 1 and a 3. 1 will be our left split. 3 will be our right split. Compare 1 versus 3. Take 1, compare 3 versus no one, and we'll take 3, and those become merged together. All right, now we have 2 sorted arrays, 2, 5, 7, 1 and 3. 1 and 3 will be our right side, and 2, 5, and 7. On the left, and we'll do like we did before, compare the beginnings of each array. 2 versus 1, we'll take the 1. 2 versus 3, we'll take the 2. 3 versus 5, take 3. 5 versus nothing, and 7 versus nothing. And we've basically merged the first division that we made way back in the beginning. So we go back up. And we will be doing some dividing again. So I'll leave this part blank. All right, we divided this range. 5 plus 8 is 13. 13 divided by 2 is 6. All right, of course. Integer math, as we are doing, gives us 2 elements. And we have 9 and 8 as single elements, which can be merged together, just like we had previously. So our red list, like before, is our right list. Compare the 2, 8's pulled, and then 9 is pulled. And those 2 lists are merged. Right? Don't have another sorted list to merge with yet. So we'll go back to 6 and 4. Those need to be split into 6 and 4 as separate lists, right? Logically speaking. This is all happening in some temporary arrays. We'll see the code for this in a minute. Right, compare 4 to 6. Take 4, then take 6. Now I have 2 sorted arrays that we can merge. We have 8, 9. And we have 4, 6. And as we had before, we'll compare the fronts of each list, 4 versus 8. Taking the 4, 6 versus 8, take the 6, 8 versus nothing, and 9 versus nothing. And those are sorted. Lastly, we have 2 sorted lists. And we will merge together, right? 1 versus 4, 2 versus 4, 3 versus 4, 4 versus 5, 5 versus 6, 6 versus 7, 7 versus 8, 8 and 9. And we are sorted. So there's a lot of data movement going on here, and because there's so much data movement, there will be a temporary array to help us with that work. Memory space will be 2 times n, because we'll need a temporary size of the array that we're working on. store values.
I have a question.
Yep.
So for the last, for line 18, we compare 1 to 4 and we get 1. And then we move on to the next orange one. It's 2 to 4 and we get 2. Same as 3. And 5 to 4, we get 4.
Yep.
And we compare 5 to 6 again.
Yeah, so before, yes, we compared 4 and 5. This 6 is the front of the list. Let's compare the two fronts, 5 versus 6, right? So there's always a front of the list versus we have a pointer, not a pointer, right? A value that's tracking where the front of the list is. And if we pull from that front, we advance it because we're consuming from that list. And it's a new front of the list.
Okay, got it. Thank you.
All right. Okay, so merge sort, recursive, pass the array that we're going to sort, temporary footprint that we're going to be working with in the bounds of the array that we are presently in, right? So initially, we are in the full range of the array. Right, so left and right. Left is 0, and right is 9. So we have a 10 element array that we're going to be sorting. And the first step, recursively divide. So the middle is now 4. Merge sort again, going from 0 to 4. Merge sort. And we keep going from the left to the middle. So eventually we're going to get to the point where we're at one element. The left is 0, the right is 0. So now we're down to this one particular element. So we get out of our first merge sort. Now we're looking at 0 plus 1 and 1. So we'll have 1 and 1. So we've finally gotten past the first step. So we are now back to All right, so we dug down to where we're at this point where we have two one-element arrays. All right, so we cut in half, we cut in half, cut in half, keep cutting in half until we get to our two one-element arrays. We're going to go ahead and go through a copy step. We're going to copy left side into our temporary, and we're going to copy our right side into our temporary array. What we're going to do here, since we're copying anyways, the first copy, the left copy is straightforward. I minus 1, I minus 1, right? Just iterating for the appropriate amounts, copying over. For the right-hand side, we're going to do a little math here. Right plus middle less j, copying from j plus 1. So what we're actually doing is we're going to swap the right side's order so that the actual fronts are in opposite ends of the array. So when we're at a single element, it's kind of hard to see and it's not relevant because we're still going to be comparing 2 versus 5 because each single element arrays. But with the right-hand side on this side actually growing to 5 and the left-hand side 5 growing to 2, we're going to be forced to stay within bounds of the arrays. I don't have to do any extra boundary checking for when we're doing the merge step.
I have a question. So for line 15, could you please let me know why we do the middle plus 1?
Or plus 1 because we've already covered the middle on this side.
On left side?
Yeah, so the middle here went to the left side and the middle plus 1 goes to the right side.
Oh, okay, got it. Thank you.
All right, so this is our entirety of that merge step that we're talking about. So we grabbed 2 and 5, compare between the two, and doing our advancing. So we're looping for the full boundary. So our left, when we get to this point, we should be 0, and right is 1. So we have 2 elements because we're doing an inclusive comparison here. So from 0 to 1, we're going to look at the front of the left-hand side, right, where I is tracking, and we're going to look at the front of the right-hand side where J is tracking. If the left-hand side is smaller, we will take from the left-hand side and I to move it down to the right. All right, so for first case here, so we're looking at 5 and 2. So that means temporary is smaller. So we're going to go ahead and pull from the right-hand side, and we're going to decrement J. So J is going to now look at 5. So we pulled 2, copied it over back into our source array. J went down, so J is now at 0. So we're comparing 0 to 0. And that's not, 5 is not less than 5. So we'll go ahead and pull from the right-hand side, quote unquote, which is actually left-hand side. Next value into our second element. So 2 and 5 are now swapped around. So let's see. Do swatches. There's K. Now let's get to this point. Unable to read memory because K doesn't have a value. That's fine. And then we have these 2 data points. I didn't, because I needed, forgot to hit my enter key. All right. And we have I and we have J. All right, so for the sample data that we're sorting in the program, all right, 12 and 71 were the first 2 values that became sorted lists. So we're comparing the two. 12 is less than 71, so that's the left side. So we'll go ahead and grab 12 and increment I and copy that over into array sub K. I increments. Now we're looking at 71 versus 71. All right, 71 gets pulled, dropped into array sub K, and our first 2 elements have been merged back together. So debug output. All right, getting back to the point where we have our elements. All right, so now we have 2 lists, right? Full range, right? Left is at 0, right is at 2. So we're looking at merging these 3 elements, right? So when we divided, we had 10. So 5 went to the right, 5 went to the left. We divided, we had 3. 3 went to the left. These 2 went to the right. And these 2 divided, they got merged together. So we have our first sorted array of 12, 71. And we're going to go ahead and merge 9 into that. Yeah, so the ternary or conditional statement, here's the exact same code as if else. All right, so if you're not familiar or haven't used this one very much, this is the same thing. So you have your test if true. All right, same thing we have here. So it's grabbing temporary I++, drops it in array sub K. And then if false, grabs that same thing over here and drops it in array sub K. All right, so I actually benchmarked this a while back because I used to think, well, it's just a shorter way to code it, but actually it performs better. I don't know what the compiler does such that this performs better than a blanket if else, but it performed better. It was like 30% better actually. So I was kind of surprised, but hey, you're never too old to learn something new.
Sorry, what is the pound if def gonna do in line 42?
Now, if print intermediate is defined, which I defined up here, that means that symbol exists. which means this code exists. So if I don't want it to spit out all this output, I could just delete that, and then the compiler would not compile this code, so it grays it out. So it actually does not exist in the code base. This is something you typically do for cross-platform compatibility or debug code versus release code. So you want debug code to spit out all the data so you can figure out why it's not working. But in release code, some data is sensitive. Credit card numbers, social security numbers, names, addresses, medical records, things like that, where you can't spit that out plain value in production environment.
And can we use just if statement instead of the pound if define?
Yes, you could control this with just a programming flag as well. Difference between that is that's a runtime decision based off of a variable, whereas this is a compiler time operation where it actually literally does not exist in the code after it's compiled. So the compiled binary would not have these print statements.
Okay.
All right, so our range is our first 3 elements. All right, so we copy them over. We arranged it so that 9 is the beginning of one list, 12 is the beginning of the other. The right-hand side is going to grow towards 71, and the left-hand side is going to grow towards 9. So 9 is the smallest, so we'll grab that over into our array. And now both both ends are actually in the left-hand side. So we're now at the largest value in the left-hand side. We have right-hand side left its boundaries and is now looking at 71, but 71 is a valid part of the array that we're looking at right now. So we're just going to be comparing 12 to 71. We'll pull 12 and then we'll pull 71. And we have our slightly larger array. And we'll keep on merging. Getting down to our 2-1 element. All right, 3 to 4. Now we're at 11 and 4. Need to be merged together. 2-1 element arrays, right? They get merged together and then get to a bigger swath. So now we're all the way back up to our first left half. I don't know how I managed to do that. Let's go ahead and kill that. All right, so our full range of values on the original left-hand side. All right, so we have 11 and 4 as a sorted list. So that's 4, 11. And these 3 values, which are 9, 12, and 71. All right, so 4 is the smallest value in the first list. 9 is the smallest value in the other list. Right, grab 4, then we'll be comparing 9 and 11. And just keep on along that fashion. The numbers grow towards each other. Eventually we have merged. And so we look at the console window. All right, it's just going to show us as we're breaking down and then creating our sorted parts. So our next output will be these 2 lists merged together, right? Grab 4, we grab 9, we grab 11, we grab 12, we grab 71. All right, what'd I do? All right, managed to get it to block somehow. All right, so our full left-hand side is merge sorted. So now we get to jump back to the right-hand side, split it in half, split it in half, split it again in half. So we'll have 24 and 181. Those merge together. Then we'll merge these 3 together. And these 2 will merge together. And then we'll have our larger sorted list. All right, so I'm just gonna let it run through. And we can see, right, so we got down 24 and 81, sorted list. Then we folded in 171 into that list. We got to 19 and 21. We got sorted and folded in to our larger list. We now have our two halves at the beginning. So 4 and 19 compare, all right? Then 9 and 19 compare, then 11 and 19 compare, then 12 and 19 compare. Then start pulling several values from the right-hand side, and we get merged. Right, so that is the entirety of the code. There's a fair amount of it. Right, and again, the reason why we invert the copying here is so I don't have to keep checking J to make sure J didn't leave the boundaries of the array. Good old recursion. So how are we doing with recursion? Right, we are our various components. Here is our base case. This causes us to stop recurring, right? Because if we don't have work to do, literally, we don't do anything if we get into this function call. And then this particular recursive algorithm has two production rules, right? Where we're grabbing, because it has two calls, right? And the rule for each call is different. In both scenarios, the middle value is what is getting mutated on each call, right? So we do our calculation in the middle, one value to the left, one value to the right. And we get to the point where left and right are converging upon each other. Oh yeah. Trying to write algorithms from scratch is definitely challenging. And this is no simple algorithm. Right, so as usual, when you're trying to write an algorithm in data structures, you want to have the drawing of whatever the data is on the right-hand side, and you want to start small, right? Because when you were trying to chop wood, it's best not to try to chop down the whole forest. Better to start with one tree at a time, right? Because as soon as that tree's done, then you can keep going and building. Eventually, right, the forest is gone. Hopefully you replant, but yeah, that's a different story. Yeah, so you wouldn't be writing merge sort code, but you might need to be reading merge sort code on a test. So you want to recognize what's happening, right? Loops, lots of loops in here, but all these loops go for quite short distances. The longest being the whole length of the array, right? So this would be half, this would be the other half. Right? The very last merge is the longest merge because left and right would be the full range, 0 through 9. But the interim work gets small, right? Especially, see how I drew it. The amount of work that we had to deal with, amount of work we had to deal with keeps getting cut in half. And we're dealing with halves, still a half. Right, that's not right. Still a half, or half a halves. Half scale of the whole thing. All right, eighths, quarters, getting to half. And then we got those two halves and we push them together. This is why this one performs very well. So let's do comparison. All right, so we have bubble sort, which is the worst in the worst case due to the number of swaps it has to do. Then we've got our insertion sort. All right. It is consistent. Only has n swaps at the end of the day. In the worst and typical and average cases. All right, best case, the list is already sorted, so no swapping at all. Insertion sort, it benefits not having to swap since it is shifting values around if needed. All right, so between these simple three, insertion tends to win out on having the least overhead on average, right? So if you watch that YouTube video, I'm sure they probably got to the point where they did ascending sorts just so you can see. Right, best case scenarios. Sometimes in best case scenarios, we have our simpler sorts win out over more or less standard sort, right? So quick sort. Okay, Q sort. C library tends to be the sort that is implemented in libraries due to big O n log n, which is the practical best you're likely to have with the sort. And we favor quick sort over merge sort for in-memory sorts because of the memory footprint that merge sort takes. All right, so why did we bother talking about merge sort then anyways? All right, other than being a practical use of recursion, quick sort is bound by how much memory we can allocate. So if we want sort 1,000,000 records, QSort should be able to handle it just fine. We start getting to the scale of 1 billion or more, then we start running into problems. Right? This would be simply impossible to do on a 32-bit system. Couldn't allocate an array large enough. Larger systems, right? 64-bit, tons of RAM. Could go bigger, but they'll be bound at some point. All right, so say we have a file of billions of data values that need to be sorted, which is a thing that certainly happens, usually happens at the database level. Merge sort can handle this problem. The recursively dividing is done on the file till we get to the point that the file size is small enough that we can sort the data in memory. All right, so say we get a large file, it's 1 terabyte, and we'll split that down to 500 gigabytes. Let's not get too big. Let's go, let's do 100 gigabytes. All right, pair of 50 gigabyte files. 50 plus 50. All right, so we can take file 1, and 2. So we'll go ahead and take file 1. 1A, 25 gigabyte file. And 1B, also 25 gigabyte file. Take 1A as we did before, break that in half. 2.5 gigabytes. Yeah, I should probably just use a base 2 number to get rid of the fractions. Who needs fractional numbers? So we'll change these back to base 2 numbers. 32, 32, 32, 16 gigs. All right, 1 AA, 16 gigs, and 1 BB, whatever we want to name them. 16 gigabytes. 1 AA, right, gets split down to 8 gigabytes. And gets split down to 4 gigabytes. 2 gigabytes. And we'll say 1 gigabyte. We have enough memory to quick sort. So we'll sort each of these 1 gigabyte files. Then we'll merge those 2 sorted files into a larger sorted file, and we can delete the 2 1 gigabyte files. All right, so we're gonna need a fair amount of disk space as we do these, and of course, this pattern can be abstracted away such that we're just reading from either end of the file if we wanted to. Just getting those 2 data sets, put them in a sorted, and then push along, but we're likely going to need an extra 125 gigabytes of space with all the files that we're going to be creating on disk as we're going in, or recreating or reusing to work through the system. But the algorithm is effectively the same. Some of the mechanics we might tweak a little bit because trying to manage a whole bunch of files is not what we want to do, and that's where the recursion we want to leverage would take care of that and help us track all the various files. But we'll continue. Get another 2 1 gigabyte files, each of which gets sorted, then merged. Then we'll have 2 2 gigabyte files that are sorted, which we can merge, and we'll continue on.
Sorry. So for 128 gigabytes, we divided to 264, and then we work on the file 1, and we divided to 232.
Yep.
and then we work on the file 1A.
Yep.
So it's
Yeah.
going to be divided to 260.
Mhm.
But why we add the 1B as well?
Yeah. So just like before, right? So we don't deal with that part initially. It's just at some point we'll come back and create. Right. So just like before, so we divide it in half. This is the half we're working on. We divide that in 2 halves, divide it in 2 halves, divide it into a half and a half. Right, those get merged together. Then we go back to the next file. That gets sorted, then it gets merged. Then we go back to the previous 2 files. They get split. They get merged together, and then we can go ahead and go back to the previous file, bigger file we created. Right. So this is like my 1 gigabyte file, 1 gigabyte file, and because we did uneven split partial file, so we have our, say, a 3 gigabyte file, 2 1 gigabyte files. They get merged together. So we've got our 3 gigabyte file and our 2 gigabyte file, and merge them together and carry on.
Yeah, I mean that why we don't get 316, 216 and 132? Because
There would be, so we would get 16s over here. So, right, so here's our 64 type thing. That 64 gets split. It'd be 32, 32. And then, right, then when that 32 got to 16 and 16, 16 and 16, it's just, we're not going to do it all at the same time because we're only going to be able to work on basically 2 files at once. So we just keep reading data from each file. So when we get to the merge step, I just read from file 1 a bunch of data, I read from file 2 a bunch of data, and then we just merge those things in memory. And then as those buffers empty up, they keep going back to the file until those files are empty, and we're fully merged. And as we're merging these things, we're writing back out to another file. So we'll have 3 streams open at the same time, 2 that we're reading from, and a third that we're writing to. And then when that step's done, then we have our larger merged file. So then it goes back and looks for more files that need to be split and sorted and then merged. And then once we got 2 files are sorted, those can be merged. And then we have a larger merged file, right, until we get to 164 gigabyte merged file. Right, so then we jump back to the right-hand side. It starts dividing, right? So we have the 64, 64, 32, 32, divide until it gets small enough that we can merge it. But all these other files that we had that were temporary and smaller, they've been long since processed. So they're just gone. We don't need them anymore. So we only need at most 3 files at any given time, the 2 that we're reading from and the 1 that we're writing to.
Got it. Thank you.
Yeah, so merge sort, there might be other sorts for file. Let's see. Best sort for sorting massive files. Let's see what they say. Yeah, can't do. I'm curious what people are saying in Stack Overflow. That's not much of a quick sort. Yeah, not marked as the answer. There's the answer. Payload sorting algorithms. Here we go. Let's see what they're saying here. AA sort. This is a slightly different use case. I'm going to see this window. I'm curious what they're talking about here. But let's go to Wikipedia. The number of ways to sort. Let's see where we can find stability. We haven't talked about that. We'll talk about that in a second. All right, a lot of sorts mentioned here. Lots of sorts. And I'm sure this is even an exhaustive list of all the different ways we can sort. Yeah, bogus sort. A bogus sort is just for entertainment purposes only. Stability is a good thing to point out here. So in fact, let me grab, make sure you guys are checking this out. Some sort sorts. Some sorts are stable and some are not. So what that means is a stable sort is going to preserve the relative order of the values as they occurred in the original data set, whereas an unstable sort may not. And if it's just a single data point, stable versus unstable doesn't matter, but there's additional data points associated with it. Say we're sorting people, and the entirety of the data is a first name and a last name, and we're sorting by last name. So we might have Bob Smith and Tina Smith in the file where Bob Smith is before Tina Smith in the file. A stable sort would keep Bob in front of Tina in that relative position. An unstable sort, Tina might end up being sorted before Bob because they're both Smiths, so they're a match. And then we're not considering in the other data point for sorting on a secondary key. So there's a single key sort. So a stable sort would keep the associated data elements in stable order. So you can see here the image. See, original data set, we have 2 5s. So the hearts coming before the spades. Stable sort would keep it such that these 2 5s are in relative order as they were in the original data set, and unstable gets them crossed over. I don't expect you to memorize which sorts are stable and which sorts are not stable. Right? If you need the sort to be stable, just make sure you're choosing a stable sort type thing. All right, we've got a lovely chart here. Best average, and of course, worst case is big O notation. Always look at things worst case. So merge sort has a significant advantage. Its worst case literally is truly in log n. We'll talk about heap sort later because that's trees. And then we have some of our simpler ones: insertion, selection, bubble. Let's see. And there's a lot of other sorts here that we are not going to get to. Right? N squared is the common thing, but n log n is as good as you're pretty much going to get. Yeah, not the next time we meet, which is in 2 weeks, because next week is the holiday. We might get radix sort on this page. Yeah, radix sort. This is an interesting sort because it is very much different than the other sorts. So I'm going to check that out ahead of time. Radix sort. Just make sure I didn't break the link. It is a different approach at sorting the values. Right. And of course, there's many options because you don't always necessarily have the one best. The one best. Okay, 1 second. Okay. Let's see. Okay. All right. Does it even have BOGO sort on here? Probably. That does have others. Under others. All right. Unbound runtime. All right. BOGO sort. If I recall, BOGO sort stand for bogus sort. It just basically randomly swaps 2 values and says, "Are we sorted?" Oh, we're not. Okay. Randomly swap 2 values. I don't remember for sure, but it's something along those lines. Just to show some really bad, education purposes. Yeah, I'm not even going to bother. Feel free to read on them if you want. There's plenty of sorts to check out. We are constraining ourselves to the ones that we've talked about. Into the 3/2, right? So that's 3/2 power. So you cube it and then square root it. Right, so it's not quite n squared, right? Because n squared would be 4/2. That's not quite n either. I'm not quite sure how that would show up on the growth chart. Log would still be faster than a half exponential notation, if I recall correctly. That's See if we can get a little calculator out and see for a second. All right, so you got 10 cubed here. No, mine to go. Okay. Just have squared, right? All right, 10 cubed, right? Square root 31, right? As opposed to, right, 10 squared being 100, right? So 10 squared is much higher, but then, of course, 10 log is going to be much smaller. You got 100 cubed. All right, going to a million versus 100 squared. 10,000 and then 100, right? Log 2 times the original 100 because we have n log, right? 200. So n log n should be much faster than n cubed square rooted, right? It's 1,000. So it's definitely better than squared, and it's not too far off the log, but I expect it's still going to grow significantly faster than our log is going to. All right. Let's see. So the test two, it's still several weeks away, but do have a holiday, so it's not, it isn't that far away. All right, so we've got next time. So I'll have the practice test ready for next time, and then test 2 will follow after that. We're mostly through it. Let me double check something here and make sure I'm not forgetting too much. Recursion and sorting. Oh yes, memory. Now I remember. Now I remember what we talked about. I remember now. All right. All right. So for the test, knowing the notation of each sort, knowing how each sort works, being able to actually sort the data based off of specified algorithm, and comparing those sorts. Are things we'll see on the test. Yeah, quick sort you won't write on the code on the test either. If I'm going to have you implement a sort, it's going to be one of the simple sorts. All right, 2.6. Multidimensional. Dimensional arrays. Okay, so let's get our baseline. All right, an array is a collection of values where we can index into the array to get to any element at any time. All right, so things that we know. So single dimensional arrays. All right, so say we do an int 10 sort of thing. And get the language to be a little bit more C++, and numbers 10. All right, 2, 5, 9, whatever values. Another 9, another 1, whatever. We're at 3, 6, 8, 6, 7, 10 elements. If we go ahead and look at memory, All right, we have zero-based indexing, and the reason we have zero-based indexing is because of the math that we're about to look into here. 2 is the first, 5 is the second, so on and so forth. And so the way it works, if I ask for the value at numbers sub 4, numbers holds a memory address, right? Arrays are reference type variables after all. At that base address, we'll find the first value in the array. Right, so 2 is the first value. Memory address of where 2 is the same as the value stored in numbers. Each value is a fixed distance from its predecessor. Right? Each element takes up exactly the same amount of space. Right? So, assuming these are 32-bit integers, aka 4-byte integers, if the value of numbers is, say, 1000, right, we have a base address of 1000. From this base, can calculate where any element is by its index. All right, so calculation is going to be, the math is base address plus index times element size. So here, given, we have a base address of 1000, element size of 4 is the address of numbers, and let's make it 5. That way we won't have too many 4s floating around here. All right, so numbers 5 being the 6th element in our array contains the value 4. So go and plug in. We have 1000 plus 5 times 4, and that equals 1020. All right, so we go and take our tables and brute force this by adding address. Let's see if I have enough space. Not quite. Let's change this to 100 instead of 1000 to keep things fitting. Right, every element is 1 greater than before it. There's our 120 that we calculated. And keep going, 124, 128, 32, 136. Right, address of numbers 0, same calculation. Sorry about that. Couldn't get my headset off fast enough. All right, so 100 plus 0 times 4 gives us 100. The address of the very last element. Numbers 9, 100 plus 9 times 4 gives us 136. All right, so the memory space allocated to numbers is the array size times the number of elements. Right, so we have 40 bytes allocated to the array, given the base address of 100, the valid byte range is 100 through 139 inclusively. All right, any of those byte positions, we would have data, right? So last value taking bytes 136, 7, 8, and 9. All right, first value to flip it around, taking bytes 100, 1, 2, and 3. All right, each one of them is 4 bytes. All right, so this is the mechanics of how a single-dimensional array works when we take this to multidimensional arrays. All right, this is an abstraction. The memory as RAM is one massive single-dimensional array. Saying that we have 2 or more dimensions is something that we're only perceiving as that memory is still going to be mapped into a single dimensional array. There are 2 ways of doing this mapping: row major order and column major order. Row major order is the most commonly implemented. And it's essentially like this document. Each line is a row. As a row fills up, we'll go down to the next line and start filling that row. All right, column major, which other languages have some similarities where you have languages that are vertically oriented. So the characters go down vertically. And as you fill a column, then you go over to the next column. All right, so that's the alternative approach. Column major would go down columns. And as columns fill, we'll go to the next column. And that's the extent of which we'll talk about column major, because it's sufficiently less common. Okay, so given we have an array defined as, let's go for numbers 7, wherever the syntax is, 7, 9. We have 7 rows, each of which is 9 wide. Right, so much as if we had numbers 1, 9. Right, so 1 row that is 9 wide. So what we did was we added 6 more rows below. Let's get our big table. Let's see here, we got 9s. That goes there, that goes to 8. Index. All right, so here we have our matrix, 2-dimensional array. This is our first element. And then down here at the end would be our last element. This would be our row end, N0, N1, et cetera, et cetera, et cetera. Right, so the calculation is a continuation of the one we have for a single dimensional array. Now we just need to account for the number of rows already allocated for the row that we are indexing into. All right, so say we want to get to this particular position. We want to see what value is at this. We still need the same givens. Givens, base, address. Let's call this one 200. Element size. We'll use 4 again. No, it doesn't necessarily have to be 4. Like if we're doing characters, it could be 1 byte, or if it's Unicode characters, 2 bytes, or if these are doubles, 8 bytes. All right, and we want the address of numbers 2, 1. All right, so we want to know where we are in the third row, and specifically second column of that row. All right, so before we dig into the full expression, how big is a row? All right, we specified matrix as a 7 by 9. 9 indicates how many elements there are in a row, and each element has a size of 4 bytes. So in terms of elements, 9; in terms of bytes, 36 is how big a row is. So how many elements are there for numbers 2, 1? The 2 indicates how many rows have been fully allocated. And the 1 indicates there has been 1 element in our current row that is allocated. Fix, fix, fix. So the total number would be 9 elements times 2 rows plus 1 element, or 19 elements allocated for 2, 1. 19 elements by 4 bytes per element gives us what, 76 bytes. And we'll add that to the base address. All right, so we got our 200 plus 2 times 9 plus 1 times 4 gives us 276 is our memory address. So if we manually do this, 200, let's drag it along down here. All right, manually check our work because that's always fun, right? All right, let's see. All right, we'll just do it manual. Keep the pattern going. 244, 248, so on and so forth. Math, math. Everyone loves math, so much, we should do it all the time. And 272, and then 276 for the person in question. Of course, we just keep doing the math. Skip along. All right. 9 times 4 is 36. Each row is 36. So this last number is going to go up by 36. So what's that? 304. 40, 376. That 412, and then 448. All right, how big was this array? All right, 7 by 9, 36. Wait, hold on. My brain can work. 63 elements. Someone check my math. Is my brain working? Monday. 9 times 7. I believe that's 63 elements. Each of which is 4 bytes. All right, so 240, 252 bytes. 252 bytes in total allocation. All right, so if we looked at what the memory address would have been, we went one more element. That would be 200 plus 252, which equals, right, 452, right, which is just one past, one less than that. And that is our 448, right, because we're going from byte 448 through 448 to 451, right? Byte 451 is the last byte that is allocated to this array. And it's always good way to check your work is to see how big is the array. Okay, it's 100 bytes. And the first element's at 100. So 100 to 200 is the max range, with that 200 being exclusive, that 100 being inclusive, where our answer could be. Right, and there's a different way we can do the math. If you prefer alternative math, base address plus size of row times number of rows plus number of elements in our row times size of element. I forgot my size of element over here. All right, we distributed out the expression, same difference. 200 plus 9 elements times 2 times 4 plus our 1 times 4 equals the same, whatever we had before, 276. So 2 dimensions isn't enough for you. Three-dimensional arrays, which we can go ahead and take a peek at after we take a break. So let's take 5 minutes. Come back at 20 after. And we can talk about three-dimensional arrays, which is a little bit of a rare occurrence, but going on mute. Let's take 5.
By any chance, are you speaking? Because you are muted.
Yeah, Professor, you're muted.
Ah, yes, thank you.
Wah.
All right, so three-dimensional arrays aren't terribly common. Two-dimensional arrays are fairly common. The screen, for example, two-dimensional array of pixels. Usually the way that this is implemented in the video card is you have a front buffer for the two-dimensional array of the pixels that are presently being presented, and then a back buffer for where updates are being calculated and written into that, and it toggles those two back and forth. So if we had like a movie or presentation going along, things flip back and forth on a very rapid basis where we do the work on the backside, and then so the work's done, we full swap, present it, and then swap where we're doing the work, and then work, things happen really fast in the computer, and it tends to be very smooth. But if some older systems, they didn't have that second screen to work on, so we're basically doing the drawing on the screen as it goes, and it's kind of like the way the lecture is going, where I'm just like typing it as it goes instead of me prefetching all this work and all of a sudden, bam, just load it up and then slam you with the mountain of data all at once. That's a more seamless transition for a visual aspect, because you go from everything to nothing and it's all there. But of course, from a data display, trying to absorb all the data at once, a little bit more difficult. You can actually simulate a similar situation like downloading an image, where you go specify your internet speed to some old dial-up 16K speed, and you try and download a 2 megabyte image. You actually see the image downloading, and go line by line as one of the ways I would typically download the data. So you'd see like part of the image, part of the image, part of the image. One of the other ways they would actually do that they'd like skip lines. So you'd see the first line, the fifth line, 100th line, so they'd skip lines. So you get a good idea of what the image is, and you keep just filling in the details in every other line sort of thing. In fact, like some TVs will work like that, where they have, it's like what, the integrated, interlaced versus the other version, I forget which is which. We got 1080i and 1080p, where they'll do, I think, interlaces every other line, so they actually update every other line back and forth. So they cut the work in half by doing it by progressive interlace. Yeah, so I forget which is which. And so you can still get an idea of what the picture is with just half the information, if half the information is spread across the full screen, right? If I like cut, right, come along here and give you half the information in this way, you get half the picture, but you're missing half of what's going on at the bottom of the screen. You have a lesser idea of what's going on. And interlace, yeah, so they interlace the lines between each other. All right, so there's different ways of managing, because there's so much data you need to process, and you know it takes so much time to process that data. So how do we more or less mitigate the data presentation? So it's unusual to go beyond 2 dimensions, but there is no limitation in the number of dimensions you can have, really. We'll see, look at some of the code here in a minute and see our septidimensional array. All right, so when we went from 1D to 2D, we needed to account for the previous rows. When we go from 2D to 3D, now we'll need to account for the previous matrices. All right, so if we have numbers allocated as 5 by 7 by 9, right? It just means we had the 7 by 9 like we had before. So now there are 5 slices of that. 5 matrices of 7 by 9. So if we wanted the address of numbers 2, 3, 4, we've passed 2 matrices. then 3 rows and 4 elements to get to the element in question. All right, so it's still the same math. You're figuring out how many elements were there before you. All right, so number of elements in the matrix is 7 times 9 gives us 63 elements. All right, there were 2 of those. So that's 126 elements plus 3 times 9 for the rows plus 4 elements in our row. All right, so whatever that adds up to being. Doesn't matter if we wanted to go 4 dimensions, 4D, for a more realistic experience. Same idea. Now we're just accounting for 3D objects. Previous states in a previous point in time, if we were actually doing that sort of dimensional space. All of which is just an extension of the math. It's just a reflexive pattern. We're not going to bother with more than 2 dimensions on the test. 2 dimensions is as far as we are going to go. All right, kill my files tab. Let's get that back. Files. All right, arrays. I'm not going to bother running because there's really not a whole lot here. All right, 1-dimensional array, as was before, 12 elements. 1's at 0, 12's at 11. Nothing very exciting. Nothing's changing here. String. Bunch of strings. Strings are reference type variables, right? So we have a pointer to where this string is, a pointer to where that string is, a pointer to where that string is, and a pointer where that string is. Each element in this array is the exact same size. Right? That is a requirement for arrays. This is how arrays work because they're backed by this mathematical algorithm to manage how we get to anything. Growing to a second dimension, right? So this is literally how the data is laid out in our single dimensional space, 0 through 9, one after the other. These first 5 data points would be the first row, and the second set of 5 data points would be the second row. If we want to work with our 2-dimensional address space, right, I from 0 to 2, and j from 0 to 5, exclusive on the upper bound, which row we want to work at, and then which column position in that particular row, and we can get to wherever we want to get to this actual 1-dimensional space. Right? It's all just a mathematical offset of whatever the memory address is that's being stored by 2-dimensional array. This reminds me, I saw some of you were doing pointers and ampersands and various things like that in Discord, so I want to bring up a quick discussion on that because that's, you know, memory mechanics. Similar idea, septidimensional array, right? In reality, this is what we would see in RAM if we just do a memory dump. First value, second value, et cetera, et cetera, et cetera. And so the first 3 values are that first row. And we have 2 of those, so the next 3 values are the next row. And we'll have 3 of those, so then we have that first row and second row in that another dimension, and then keep on going, but we didn't bother allocating. Of course, this is going to be quite the big array. You have to multiply all of these together, so whatever the product of that is how much memory we've allocated. Let's remember, this is all rectangular arrays that we're talking about. Should not to be confused with jagged arrays, which we'll be seeing when we do start doing our graph matrices in several weeks. Let's see. Right, there's nothing very exciting about this code file other than show you the syntax in C++. But it's just all math, and that's what gives us the random access. Now, while I'm remembering about it, void pointer int star x equals 5 after we dereference it. Void pointer int star x, because we like to make our brains cry. And void alias address x. Right, x equals 5 and star p equals address of x. And that should be good enough. And let's see. Space on my syntax. Actually, I don't think anyone's doing pointers there. We're doing stars and ampersands, which are offsetting effects. Let me think. Pointer. So I probably need a double. This is where my brain likes to seize up. Spit it out. And we will call pointer with the address of x. All right, let's spit it out again. All right, so let's get our baseline, regular passing pointers. What I already broke it. No, 5. I set both to 5. That's not helpful. Let's make you 15. All right, so we gave the address of x. And in here, we dereference our pointer, go to where our variable was in memory. In fact, let me just change this to y. So keep things nice and separate. And because these x variables, oh, there's a nice auto. Right, these x variables are local variables, completely separate from everyone else. Do the alias next because that one is simpler. When we're doing an alias, basically this is we're messing around directly with the symbol table. So with this ampersand syntax is basically saying we are using the direct symbol table of where y is in memory. So this x is literally y in memory. There's no pointer middleman. It's literally the same entry in the symbol table. So it's representing the same location in memory. So whatever the memory address of this is, it should show up the same. In fact, let me see if I can spit that out. See out. Just x. Alias address. See if I can get this to work. I'm not going to make any promises on this one. And see out my address. Address of y. Line. Let's get white spacing consistent. Let's see if I can get this to work. All right. See, there we go. Same memory address. Because they're basically literally the same variable as opposed to storing a memory address and then dereferencing the address with a pointer. Right, it's a star means a pointer to a pointer. So we can go ahead and do pointer address of p, because P is a pointer, so the edge of the pointer is, that's an extra star. Remember the stars and the ampersands go hand in hand. And let's see if I didn't break this. This is where my brain likes to get a little fuzzy sometimes. All right, so we set it to 24, so things worked out. That's always good. But and this first two cases, these x's, they're completely separate variables. All right, x holds x, and here, call this one px holds x, and run it again. All right, so y and its alias, literally the same location memory for those variables, whereas x is holding on to that memory. So the value of x is where y is. We need to dereference x to actually get to y. And then px is a pointer, which would probably be this, should be the same, not probably will be the same memory address of p. So who did I do that there? Pointer, pointer. So we can do see out, pointer, and p, if I get enough arrows. All right, so we should see those the same value. If we were to actually print them out, I forgot they didn't actually print it out. Px hold star px, which would be the actual pointer. Okay, so there we are. Star px holds the value of our pointer, which is the value of our pointer. It's just an extra level of indirection. It just means you do an extra hop to get to the actual raw data, where our raw data is this one and only y. Raw data being our simple types. Simple types are what actually holds data. Everything else is just a memory address where we can find that data. And so if you do something along the lines of int a equals star ampersand x. All right, this is basically just doing a circle. So I'm spinning in a circle to get back to where I am. A is, and whatever our last value of x looks like 24, so that should spit out a is 24. X is declared. Indeed, you're called y. Let's try that again. All right, a is 24. All right, so if you're getting stuck on some of that, remember, parameter passing is just this, the assignment operator. It's doing the exact same thing that the assignment operator is doing here in main. It's copying the value that's on the right-hand side, the left-hand side, right? The exception being the alias here. The alias here is, directly working with the symbol table to get it set that basically we have two names into that table. All right, and symbol table. If I could type, fortunately, it did that for me just fine. Let's see if we can find a nice presentation of that. Right, here we go. Symbol table. Right, so 1 is the name of our variable, which is the symbol that represents the location of memory. All right, of course, that has a data type, and then there would be where that data is being stored. And it is a stack variable, global variable, all that other fun stuff. Leave that as an aside. Any other general questions at the moment? All right, test 1 metadata. These numbers are a little bit off. I went before class and I assigned partial credit for the double linked list question since that auto grading does not do partial credit. So the average would probably be just a little bit higher than this, probably 85%, not much different. All right, with 2 people I think this graph is pretty bad because it doesn't actually tell me how many are each, but you know, there's like 1 at this level, so we have 2 at full credit, many in the 90 range, many in the 80 range, et cetera, et cetera, et cetera. Are there any particular questions you want to see the metrics for here? All right, so here you have on the right hand side the average score on that question, right? So that's just over 90% for that particular question, 90% there. This one's 75%. Right, the big annotation of adding to a queue, which is NQ, through some of you, which somewhat expected because this question is formed in the critical thinking. Marcus is the critical thinking question, right? It's not just asked in a vanilla way, what's the annotation for NQ, right? It's not just asking you to memorize the answer and then dump it out. It's asking you to think about the question, analyze the question, and then put the answer together. So you'll very often see some questions on the test that are phrased in that way, where it's not just what's the annotation for NQ or DQ or push or pop. It's asked in a slightly more generic way. Which just means you need to pause for a second, think about what it is, right? And you see 75% of you did all right on that. Carrying on, right? The functional notation questions, things didn't go terribly well. I think it's the same code I had as on the practice test. So I'm not too sure what we're hanging up on for this one. So please let me know what is not straightforward or confusing, or what is confusing, whatever it is to make that line up a little bit better, but otherwise things are more or less in line. And this one should actually be like 2.6 after I adjust fill in the blank. I like how the report just says the blanks. So that was the, you know, B right, C left, whatever we had for that one. And this one, yeah, look at this earlier, we definitely got thrown off by, right, when we start at 1, that means we skip, we're 1 less on this and we're 1 less on this, which means we lose this +2 part and we go down to the 2n. 2n plus 1 would be possible. We would need to make that an equality. And 2 plus 1 is kind of harder, actually. I'm trying to think we can actually give the 2 plus 1. Because whatever we do to affect the test here, that's going to also have a similar effect there. But otherwise, that's the metadata on the test. Test 2 is going to be the same idea, just different context area, going from doubly linked list, recursion, sorting, and our multidimensional, single-dimensional, multidimensional array addressing. Between now and next time, the practice test will become available for you to work on that. Otherwise, we should be through what is going to be on test 2. Let me double check. Yeah, binary tree labs up next. Program 1, I have a lot of grading to do between the sort lab and program 1, so for sure that'll be done by before the next time we meet. Hopefully I'll have it done before the end of the weekend. The program takes a bit more time, well, quite a bit more time to grade than the labs do. But that's where we are overall in the class. Still have no questions? Everyone's confused, so confused, or everyone's just, you know, sleeping on the screen, waiting for the recording to play it at half speed, or I'm going too slow so they can play it at double speed. I'm talking on mute again, no one can hear me. right, fire your question away. What's the benefit of just giving internal understanding of the system? Right? It's not usually when you talk about arrays, you don't dig into how they work and how the different systems might. It's funny. It's a really old show now, but there was this TV series called 24, which you may or may not have heard of. There's actually an episode where they bring up that one system was in row major order and the other system was in column major order, and then the system's kind of just like choked to death on it because you have to do a matrix transformation to get those to line up. And matrix math is going to be a math that you're with high probability going to be dealing with in computer science, probably as a junior or a senior, assuming you're going for a bachelor's degree. So for the most part, it's foundational. So you have a good foundation of what a matrix really is in the computer. Because if you're going to need to translate that, especially if you do graphics processing type classes where matrices are the common data type, right? And these are they're arrays. So our common foundations for our data structures is they're either going to be array based or they're going to be link based or possibly a composition of the two, right? So multidimensional arrays is an extension of arrays, and we will be swinging back to the matrices again later when we get into graphs, because it's one of the ways that we can represent a graph internally in computer memory. So we got to make sure. So for the purpose of this class, it's mostly foundational, plus it's foundational for higher and deeper levels of computer science. All right, it's just one of the things that we make use of and build on top of quite often in our applications. And that's not used all over the place in our application code, but it's usually has some level of involvement somewhere. Other questions before we move on to section 3 of the course? All right, trees. A tree is a non-linear data structure. Generally, view a tree as a connected structure where you have a node that represents the data, and that node tracks other nodes in the structures. In the structure. Okay, so you may have a whole bunch of fun terminology here. Children. These are nodes that belong to a parent. All right, descendants. In fact, let me just draw a tree here. Let's get a tree. And we'll arbitrarily name them letters of the alphabet. And then we'll get some links here in a second to show the relations. Right, so when we get to it, A will be known as the root of the tree. It is our entry point into the data structure, so it's analogous to head or top. Right, so in this example, B and C are the children of A. Descendants, right? So these are nodes that we can trace down to from a node. In the tree, so all the nodes in this tree are descendants of A. G and H are descendants of C and A. There's a lot of terminology is similar to the family tree terminology you would see. All right, you could mention cousins or aunts, uncles, aunts and uncles, but that is less used. Top of the tree is called the root. From that, okay, 1 second. All right, from the root, we can get to all other nodes in the tree. All right, so a non-linear structure, since it's going to be a non-linear structure, we have various non-linear algorithms to deal with this. All right, link for that. All right. Plenty of terminology. We're still going to be working through, again, abstract data type, like most all our fun stuff. We will get to all that in due time. Talk about some tree metrics. First, which is going to be height. Height describes the entire tree. It is represented as calculated as the length of the longest path in the tree from the root. All right, so if we go ahead and start drawing some trees. Right here, there's a single path. The above tree, we have one path from the root that takes us to be the height of the tree is 1. Note, some authors describe the height as the longest path plus 1. All right, so in our class, we're counting it as 1, and we'll see in a minute why some will prefer not adding or to add. Change the names of these nodes just because. All right, so this is the longest path in our tree. That controls how high we are. So above tree has a height of 2, right? So for example, just like your height, if you have one leg that is 1/4 inch longer than your other, your height's going to be driven by your longer leg, right? If you run into a landmine or something like that, and one of your legs gets substantially shorter than the other, again, your height is still going to be driven by your longer leg. Trees are the same idea. We want the longest path that we can find. It doesn't matter if there are multiple occurrences of that length, a large number of shorter branches in the tree. All right, still have a height of 2. Still 2, length of the longest path. So a single node tree. Which I'm not going to bother to label. Our height is 1 less. That's before when we had 2 nodes. Our height was 1. So a tree that is 1 level shorter is going to be 0. And this makes an empty tree as a height of -1, which is why some authors add 1. But I don't add the 1 because -1 is a perfectly good indicator of the absence of the tree. Right, so height is a characteristic of the tree. Another thing we can look at are tree levels. It is a similar concept. A tree generally comprised of multiple levels. Level is defined as all the nodes that are the same distance from the root. Right. So the root is at the first level. Some label this as level 0 and some as level 1. Whichever way you number it, it's still the first level. Just like an array, the first element is the first element. Whether you're in a 0-based indexing language or a 1-based indexing language, the first element is the first element. The children of the root are in the second level. Right, the grandchildren of the root are in the third level. One word, okay. Right, so if we look at another tree, start tossing a bunch of them into the tree, and we'll start building a few levels here. All right, so the initial generation has the root, subsequent generation has 3. The next generation then has 6 in its level. And we'll label these arbitrarily, just going through the alphabet. Right, so our first level nodes are A, second level nodes, B, C, and D, and then our third level. It happens to be everyone else as we have this particular tree. Right, so both height and levels, right? This particular tree has 3 levels. The height of the tree is 2. If there was a 4th level, then the height of the tree would be 3. If there was a 5th level, then the height of the tree would be 4. That's one of the other reasons why some authors do the +1. So they say the height of the tree is the same as the number of levels in the tree. But here we have a one-off relationship. Right, so tree height and the number of levels in the tree are proportional. Proportional. You okay there with our tree terminology? One of the things we can do now is at the tree, look at node characteristics. Into node characteristics. All right, so a node would exist at a given depth from the root, where the root is at depth 0. It is 0 away from itself. The root's children would be 1 away. So their depth in the tree is 1. Again, grandchildren would be 2 away from the root. So their depth is 2. All nodes at a given depth comprise a level of the tree. Right, so tree level and depth are similar terms. Level represents a layer in the tree or a group of nodes in the tree at a given depth. Right, so a node has a depth. Right? A node does not have a height. A height is a characteristic of a tree. So you want to be careful with terminology. All right, so depth is our key term here. Right, paths in the tree are a sequence of nodes. For the root, there is no path, as that is where we would start. In the tree, but we may build a path from the root to another node down in the tree structure. Let's see. Go grab, or at least point out tree section. Here we have some of our terminologies as well. All right, so like we saw before, level 0 on the test. I'm not going to label these as 0, 1, 2, 3, but just to give a concrete number. Right, one of the things to point out, leaves in, that's what I meant to say earlier. Leaf node, it's a node that has no children. also known as an external node. Right, so leaf, much like a tree, there's no part of the tree that extends beyond the leaf, right? And the branches or the paths you got to that leaf. Internal node, basically a non-leaf node, or a node that has one or more children. Let's see. All right, paths, we just talked about that. Binary trees we're getting to, and height and depth. All right, make sure I wasn't forgetting anything. That we're getting to in a second. All right. We're okay for the moment on our terminology. Looks like now is a good time to think about a 5-minute break so you can try to absorb something or go up to your brain out, make some space for some more trees. Got to plant the seeds and let them grow. Because tree analogies since we're talking about trees. Eventually we'll start building these trees in the forest. So going on mute and we'll be back in a few. All right. N-Arry trees. N is a bounding condition or how many children a node is allowed to have. Right, so generally most trees will fall under the category of an N-Arry tree. It is needed such that we can actually construct such a tree. So if we're to look at code for an N-Arry tree, a bounding, just saying we're within the boundaries of that, right? So like property boundaries, right? While you're in your property boundaries, you're not trespassing in your neighbor's house, sort of thing. All right, so we'll have whatever our data is. And again, we're just being generic or simple rather, and just using an int. And if we want to have a bunch of nodes, array of nodes, sort of thing. And we probably want to say, we have our size item, right, and corresponding constructor. Size. So we can create a node of such a size. That's if we were to, right, so say we wanted a 5-array tree to be supported. Go ahead and draw 5-array tree. So with 5-array tree, however many nodes we have, wherever they end up being, let's make a big one here. And put a couple on that side, and that's pretty good enough. All right. So we have our root node. It has 3 children, so that's within the bounds of 5. We have this node that is tracking 5 children. All right, so this is our 5-array tree. And it's 5-array because of this particular node having 5 children. Right, so we're going to actually draw that data structure out. All right, looks something along the lines of this. We have a bunch of links. To all the nodes that are its children, sort of thing. All right, just pointers to wherever their children are. Right, this is our array of elements. In fact, I guess I should go ahead and attach them all together since it is an array. All right, index 0, 1, 2, 3, and 4 for our array of elements, and whichever node they point to, and of course those nodes would be of the exact same structure. Let's see if I can shrink this down. Let's at least. Bound it that way. And then scale down as best we can. And try to squeeze them all in here, which kind of sort of the same thing that we'd be doing in memory. Because this is a fairly large node type. And even if we have nodes like we had in our original drawing, it's all our leaves are going to have these empty arrays. And all of our tree nodes, right, the root is going to have two elements that are not used in the array. This node on the right hand side has three elements not used, and then all the leaves are going to have a bunch of empty arrays. So depending on how you're doing the allocation, right, if you're allocating the arrays ahead of time or in the lazy approach as needed, you can be wasting a fair amount of space on the heap, just trying to maintain this tree structure. Not to say that this type of structure isn't unused, but usually when the airiness gets to be beyond 2, we're going to be enforcing additional rules on the tree structure so that we aren't wasting that space. Right, but so N just represents the max that we're going to support. So every time we come along and construct a node, we would have a size that would be consistent for all the nodes in the tree structure. Okay, so this is very, very generic. Go ahead and do 3.3a binary trees, which is an N-Arry tree of size 2. Right, so a binary tree is an N-Arry tree where N is 2. We use binary trees because the node structure is the simplest node structure we can have. That we can have. We have the data element and 2 pointers. One pointer represents the left subtree, and another pointer to represent the right subtree. And data binary node star left and binary node star right. And that is our tree node. It just keeps things simple. The code is, this is as small as you're going to get for a tree. Right, the next level smaller would be a singly linked list going in one direction. So this node structure literally is identical to a doubly linked list node. You have 2 pointers. A doubly linked list node, you typically have a previous and a next. Here, instead of going forward and backwards as the common way that doubly linked list is used, we're going to go left and right. All right, so let's draw a couple sample binary trees. All right. It's a binary tree, binary tree. Binary tree, once I get some links in here. All right, so we'll call these trees A, B, and C. All right, so binary tree with just a single node, A. It's a root, A is the root, and it's got no children. Right, the height would be 0. We have another binary tree here. The B is the root. It has just a left subtree and an empty right subtree. So our first case, we had 2 empty subtrees. C over here, binary tree as well. C has a left subtree. Its child has a right subtree. And we know from the drawings left and right, just based on the orientation of the links, links going to the left represent left subtrees, links going to the right represent right subtrees. And just make some bigger ones. Because a bigger tree is a bigger tree, right? Maybe, maybe not, depends. Binary tree, and we can confirm it's a binary tree just by looking at every node in the tree. All right, so we look at this node, has 2 children, so we're good. Look at the next node, 2 children, good. Node over here, 1 child, that's bounded by 2, so we're still good. 1 child bounded by 2, still good. And then we have these as leaves. All right, so this entire tree has 3 leaves and 4 internal nodes. Right? So everything that's not a leaf is internal to the tree structure. All right, so we're going to be having a binary tree lab. So let me bring that up, so show you where we're going. Okay, back to where it was. All right, this one's going to be an array-based tree. People like to get hung up a little bit on array-based trees, so let's dig into that. Array-based trees are slightly less common than link-based trees, as we saw with the class node structures we had before. Array-based trees. So let's talk a little bit about this one. Based trees will have the root at index 0. The next level of the tree would be the next elements in the array, and we'll continue along with that fashion. Right. This pattern is used for any sized N-Arry tree. So specifically for an array based binary tree, each level is twice as big as the level before it. So the root has 1 node, right? This is the first level. First level. Yes, put the last. First level. The root. Second level. We have 2 nodes. No, this is going to be a single dimensional array. Third level, 4 nodes, etc. The the child of a node is calculated by 2 times the index plus 1 for the left child and 2 times the index plus 2 for the right child. All right, so we have the root at index 0. Its left child is at 2 times 0 plus 1, and its right child is at 2 times 0 plus 2. All right, so let's do a drawing and the table to show that. A, B, and C. And since this is array-based, I'm going to use an arrowhead. Get our table. Index, a little bit too big. Index and data, right? The root is at 0. Left child, who's B, 2 times the root, which is 0 plus 1, B, and then C. Go ahead and grow the tree. And we'll do so only just partially. Reliable these D, E, and F. All right, so we have 6 data points here. So go ahead and insert our table. And I'll leave a blank space at the end. Our data. So A is our root still, B and C are its children. Right? B's children are D and E. D is going to be 2 times its parent plus 1, since it's the left side. B is at index 1. So 2 times 1 is 2 plus 1 is 3. That's where D is. And the right child will be right after that. There's E at 4. C, who's at index 2. F is its left child. 2 times 2 is 4 plus 1 gives us F. Right, so a 3-array tree, array-based tree would have, again, root at 0, first child, 3 times index plus 1, and then so on and so forth, same idea, just one more than before. Just whatever that arrayness is, it's basically replace this number, and as we get further, there's one additional slot to account for. Right. Going back to binary. Be careful for holes in the tree, gaps. We're going to come along here and let's say we pruned off D. Right, it's the exact same tree as we had before, less 1 data point. I deleted D, so come here and delete D because there is no left child of B. 2 times 1 plus 1, 3. Subtree is empty, just like we hit empty over here for C's right child. Right, if we start labeling by levels, level 0, 1, and 2. Right, the next 8 elements would be level 3 or the 4th level, and would grow on in such a fashion. If there's some sparseness in the tree, which means we have, a little bit of dead branches going on there, you might see large sequences of empty values, which is one of the reasons why it's not common to have array-based trees. Most often we're going to have link-based trees. But this is how we do it. One of the advantages, though, we have all right, so we can back calculate who our parent is. And taking our index and doing some math can go back up the tree directly. Right? Link-based trees, you can't go back up the tree directly. You have to rely on the recursive call stack or other mechanisms. We also have an advantage of finding the last position for some structures can be quickly gotten to with an array-based tree, and we'll see that when we get to heaps. Okay. Well, a dynamic array, depending on what you mean by dynamic array, is still just an array. It's going to have a fixed size once created. If you're talking about like a vector, which is a scalable array, where it resizes itself, that's still the same thing. Your random access, all the fun stuff. It hides away the resize work for you at the expense of the overhead of every time we add a value, doing a resize, all fun stuff, which is right. You're always going to have the problem with arrays, whatever you're working on. All right, getting around in a tree. Which we're going to call traversal. 5 here, right? Okay. Tree traversals. Navigating a tree would always start from the root. Then from there, we'll work our way through the subtrees in a recursive fashion. So let me go grab this tree that we have here, reuse that. There are 3 orders in which we can traverse a tree. Pre-order. Here we look at the data in the node we're in. Then we'll proceed the left subtree, followed by the right subtree. So we'll go ahead and do a pre-order traversal on this tree, what we'll do is find my annotation. All right, so we start at the root, and we would just go ahead and spit out A to indicate we went to A. Next step, go left and repeat the process. Right, so it's a recursive algorithm. When we get to a root, go ahead and output the data there, and then we'll proceed left. Right, B's left subtree is empty, so there's nothing to actually do there. So we'll come back to where we were, and then we can proceed to its right subtree. When we get to a node, do the same thing. First thing we do is inspect the data, in which case we'll just spit that out. Left subtree goes nowhere. Right subtree goes nowhere. And we've completed all the processing for this node. So it means we can go ahead and go back up the stack chain, gets back to B, where we've also finished all the processing. Takes us over to A. We just finished A's left subtree. Now we can go ahead and go to its right subtree. As soon as we get to C, spit out the data. Left subtree, get to F, spit out the data. Once we're done spitting out F's data, traverse left subtree and right subtree, which are empty because this is a leaf node. And once F is completed, back up to C. Then we'll go to C's right subtree, which is empty. And then back up to A, and then we have completed our traversal. Right, so we went A, B, E, worked our way back up, CF. In order traversal, it's going to be very similar. Same operations, we're just changing the timing of the operations. Here we will go ahead and do left subtree, traversal. Then we'll inspect node data, which we just do as printing. Then right subtree, traversal. Okay, just like infix notation, the work is in between the data. So I'm going to do that again. So we start at A. First thing we do is say go left. When we get to B, it's recursive. Same thing we do once we get to B, we say go left. There's no left, so now we can go ahead and spit out B. Third action at B is to go ahead and go right. Right, E, repeat the same 3 steps. We want to go left, inspect the data, so we'll spit out E, goes right. Completed E, it's done all 3 operations, left, visiting, right. Back up to B. B, we've finished doing all 3 things. We traversed left, we looked at the data, we traversed right. Back up to A. We've now finished the left traversal of A, so we can go ahead and spit out A's value. Move along to the right side. Go left. F has no left subtree. Output F. Do the right subtree next. Very terrible looking arrowhead. Brings us back up to C, where we can go ahead and spit out C, does its right subtree, and then back up to the root, and we're done. Lastly, we have post order. And it is the same 3 steps, except we'll go ahead and move up that right subtree traversal. So we're going to do all our traversing before we start looking at data, which basically means go to the first leaf. and then drop that leaf off, and then we'll do something. So left is the first operation, left from B, then it says right, get to E, go left, nowhere to go right, nowhere to go. E is our first leaf. So we can pretend like it's not there at this point because it's completely processed. Brings us back up to B. Both subtrees of B are completely processed. It's more or less a leaf at this point. And we go and spit out its data. Brings us back to A. We've finished the left steps. Now we'll go ahead and go to the right step. Go left. Brings us to F. Nowhere to go on the left side. Nowhere to go on the right side of F. It's a leaf. So go ahead and spit it out. Go back up. Basically pretend like F has been removed from the tree, which makes C a leaf. But we do have a right subtree to process first to confirm that that is a C or is a leaf. So we'll spit out C at this point, brings us back to the root. Left subtree and right subtree have been processed. So my poorly drawn A now has a chance to be written out onto the screen. Get my screen grab and dump that out. So depending on the tree structures we look at, some of these little traversals will make more sense than others. Pre-order traversal tends to be more common. Usually you look at the data before you keep going, but that's not always going to be the case. As we look at other tree structures, we'll bring back which traversals provide meaningful value. Okay, now, right, this is due the 22nd, which is after the holiday. So the due date is going to be soft for this lab because I don't want you to be doing a bunch of reading. Between now and then, you probably be able to work on it just fine. And let me point you to our link-based code. Right, also have a Traversals lab do that week, which is also a soft date because of the holiday. And it's just basically extending that other lab, doing all of them. And you see it's not submitted. You want to make sure you can do all of the, be able to recognize and or write all the code for our various traversals. Right, yeah, with President's holiday next, let's see. I know my boys have 2 days off. What do we do? Yes, we also do 2 days. So you have no Friday classes this week and you have no Monday classes next week. And what does purple mean? Yeah, Tuesday's off as well. Interesting. Yeah, so you have a little bit of a gap coming up here to catch up on whatever lake or get ahead if you're caught up. Or do both, catch up and get ahead. Yeah, because here we are, Valentine's Day and President's Day coming along, right? And then a month from then we'll have spring break, so basically pretend that week doesn't exist. So yeah, so code in the file section under trees. Let's see, binary trees. Just bring this up on the screen because we're gonna be running into lab time here in a moment. Right, so here we got node-based tree structure, 2 name pointers as we saw before, left and right, data section, default constructor that just sets everybody to nothing, which is good when you're adding a leaf, which this constructor also does, except allows you to pass along the data part. Everything's public, right? Encapsulation is a joke in our sample code here because don't care about that, care about the structure. Binary search tree is going to be one of the places where we're going to start using our rooted trees. But let me get down to the traversal part, which is what we've talked about, our traversal. All right, so here's the basic signature of a traversal. It is a recursive method, so we have our recursive calls here. Where we go ahead and process left subtrees and right subtrees, and then at some point in time, we're going to go ahead and look at the data, which is just printing it out. So to make this a pre-order traversal, we move this line of code up and of course change the function names to be the same function as the new function we're creating. And our base case is that the pointer that came in here is not null. So say the tree is empty, the root is null. We try to say to traverse the tree, and then we spit nothing out because there is no tree. Our production rules, right? We change temp from being temp to being the left subtree, or temp to being the right subtree. Right? All of our good components, right? The recursive call, production rules as it stands here, and our base case. Right? Pre-order, post orders, moving timing, changing names. There's also the reverse direction, where you could be processing right subtrees first instead of left subtrees. I can't say I've actually ever seen where we want to traverse right first instead of left. I suppose perhaps we're doing some parallelization. So we have one thread working on traversing down the left, and we have one thread working on traversing down the right and collecting data. And then as they work their way back to the top, then they share that data back to the main thread. So there, I can see some possibility there for you trying to do parallel activities, but parallel coding is even more rare of that time. Usually when you have parallel coding, they're working on just desperate things, so you don't have to worry about coordination. But next time we will meet, we will spend more time in this code file and talking about binary search trees, ordered trees, because unordered data tends to be a little bit useless. So we want to get some order into our tree structures. So since we're not meeting for class next time, I'll be sending out a bunch of links to do some reading on. So we make sure we're keeping pace before the end of the semester, but otherwise, the rest of tonight will be lab time and the break time. Any questions before we roll into that? I do want to point out radix sort, since it happens to be a sort algorithm I actually use in the real world, but the physical world, not the computer world. Just want to see if we have any questions before we roll into that. Okay. Radix sort. There's a couple of different ways of doing this. There's a card game I play called Magic the Gathering, and some of the cards are cards. I sort them based on their card numbers. So they have 2-digit card numbers, right? 1, 2, 3 up to 70, whatever the numbers are. And the way I sort them, I'm actually using a radix sort where I sort all cards 0-1 through 0-9 as a pile of cards, and then all cards 10 to 19 as a pile of cards, all cards that are 20, 29, et cetera, so that the first digit, the most significant digit, which we will zero pad, I use that to sort the 0s, 1s, 10s up to the 9s. And then once I have those 10 piles, then I can then sort each of those piles. So I have 1 through 9, so I can again make my 10 piles for 0 through 9, then have all the cards together. Then that pile is sorted, and I can do the same thing with the next pile, and then that's sorted, and then add that to my sorted stack, and then it's a radix sort. Right? Insertion sort is actually another sort that we're actually in class meeting class, one that I would do with the tests, right? So I would sort them by name. So I take the first person, all right, it's Bob Smith, and I got Anna Jones is next. Anna Jones I insert on top of Bob Smith because Jones is before Smith, and I have Carla Zimmer, right, goes to the bottom. I literally do an insertion sort. So some of these simple sorts are actual sorts that you might actually use in real space time. right? A bubble sort, I can see doing that way. Sometimes some people will do actually an insertion sort. They'll look for who's the smallest. Okay, grab it, set aside. Who's the next smallest, right? It tends not to be terribly efficient, but if it's a fairly big stack, right, trying to maintain the sorted part becomes a little bit unwieldy, trying to thumb through and say, okay, where are we in our sorted list? So these sorts don't necessarily just have practical use just within the computer system. Some physical systems may actually make use of the sorting mechanics. Right, so the way that the sorting happens, it doesn't actually compare values to each other. It's just looking at the value and comparing it to the bucket that it belongs into. So it just creates buckets, right? Anything that says 0 goes in the 0 bucket. Anything starts with the 1 goes to the 1 bucket, and just dumps them into the buckets. And then depending on how many digits is our longest key, that's how many times we have to go through the buckets again, because then we'll go based off of the next key and then the next key and the next key. And then it's all nice and ordered. All right, so let's try to look at the tree labs. At this point, there's more reading to be done before we really want to dig into them, but we have a few breadcrumbs to work on. Oh, that's fun. That link doesn't work anymore, so I need to figure out where that data went. All right, I'm gonna leave that note to myself. Lost my trees notes. Otherwise, have a good night. I'll see you on Discord and again in 2 weeks.
Thank you, Professor.
Thank you. Have a great night.
Thank you, Professor.
Have a good night, Professor.
Thank you, Professor.